Hello everyone, in this video I'm gonna work on a tutorial for the second homework assignment. So let's get started. In the first problem, we have to show that 1 plus 3 plus so on plus 2 and minus 1 is equal to n squared for all n in n. And first of all, we want to show that we want to understand what it means. Okay, so 1 is the first odd positive integer and 3 is the second odd positive integer. So the left hand side here is the sum of the first n odd positive integers, and it turns out that this sum is equal to n squared. Quite interesting. Say if n is 1, so 2 times 1 minus 1 you have 1, right? So the first odd positive integer is 1. 1 is equal to 1 squared. How about 1 plus 3? 1 plus 3 is 4. 4 is 2 squared, right? And the next one, 1 plus 3 plus 5 is equal to what? 1 plus 3 is 4. 4 plus 5 is 9. So 9 is 3 squared. Quite interesting. So we can show that this is true for all n in n. And let's go ahead and use mathematical induction to prove this. When n is 1, the left-hand side is just 1 because you only have the first odd positive integer. And the right-hand side is n squared, which is also 1. Okay, so the identity holds true when n is equal to 1. And then in the inductive step, we assume that 1 plus 3 plus so on plus 2k minus 1 is equal to k squared, where k is a positive integer, which means that this is true when n is equal to k, right? So we replace n by k. And we have to show that this is true when n is equal to k plus 1, meaning that 1 plus 3 plus so on plus 2 times what? K plus 1 minus 1 is equal to k plus 1 squared. And remember that this is 2k plus 2 minus 1. So it is equal to 2k plus 1. Okay, so this is the inductive hypothesis. And this is what we want to prove. Okay, so our strategy is to use the inductive hypothesis to prove that this is true. Okay, and the last identity can be written this way because I mentioned before that this is nothing but 2 times k plus 1. Okay, so we want to show that this is true. And our strategy is we start from the left hand side and show that the left hand side is equal to the right hand side. So the left hand side is nothing but 1 plus 3 plus so on plus 2k plus 1. And it is very important to know that the number before this number is 2k minus 1. The previous odd integer, this is 2k plus 1. 2k plus 1 is an odd integer. The one right before this number is 2k minus 1. The difference is 2. Like the number in front of 3 is 1. Okay, and by the inductive hypothesis, 1 plus 3 plus so on plus 2k minus 1 is k squared here, right? So we're going to do a substitution. So this is equal to k squared. And then you add 2k plus 1. And this is k squared plus 2k plus 1. We factor out to have k plus 1 squared. Therefore, by induction, the identity holds for all n in n. Interesting. Now, let's move to the second problem, in which we have to show that 7 to the nth minus 1 is divisible by 3 for all n in n. The base case is quite simple because when n is 1, 7 to the nth minus 1 is 7 minus 1, which is 6. 6 is divisible by 3 because 6 divided by 3 is 2. Okay, and in the inductive hypothesis step, we assume that this is true for k. That means 7 to the kth minus 1 is divisible by 3, where k is a positive integer. And then we're going to show that this is true for k plus 1, which means that 7 to the k plus 1 minus 1 is divisible by 3. Okay, so because 7 to the k minus 1 is divisible by 3, we can rewrite it as follows. 7 to the k minus 1 is 3 times m, where m is a positive, where m is an integer. Okay, so again, because we can divide this number by 3. By definition, it is 3 times something, where something is an integer. So we can denote that integer by m. So this is equal to, this is nothing but this. We can rewrite this equation as 7 to the k equals 3m plus 1 by moving minus 1 to the right hand side, or adding 1 to both sides. So this and this are just the same, and they follow from the inductive hypothesis. So this is what we have. And now let's focus on the goal. The goal is to show that this is divisible by 3. So we are going to show that it's 3 times something, where something is an integer. Okay, let's do it. 7 to the k plus 1 minus 1, as usual, is 7 times 7 to the k. This is a very important observation. And then you subtract 1. Okay, and remember that 7 to the k is equal to 3m plus 1. So we just do this substitution. We replace 7 to the k with 3m plus 1. So 7 times 3m plus 1, and then you subtract 1. This is what? 21m. Okay. 7 times 1 is 7. You subtract 1, you have 6. So 21m plus 6. You factor out 3. You have 7 plus 1 plus 2, right? Okay. This is 3 times something, where something is j. Okay. So set j to be this. And it is an integer. Why? Because m is an integer. So 7m is an integer. You add 2, you also have an integer. Therefore, you see that this is 3j, where j equals 7m plus 2 is an integer. By definition, 7 to the k plus 1 minus 1 is divisible by 3. Okay, so we have proved that this is divisible by 3. By induction, this is true for all n in n, and then we're done. So easy, right? Okay. So let's move to problem number 4, which is more difficult. Okay, in problem number 4, we have to prove that if a is greater than or equal to minus 1, then this is true. 1 plus a to the nth is greater than or equal to 1 plus n times a for all n in n. And this is called the Bernoulli inequality, a very well-known inequality. It means that no matter what n you plug in here, as long as a is greater than or equal to minus 1, the left-hand side is always greater than or equal to the right-hand side. The base case is quite simple, because when n is 1, the left-hand side is what? 1 plus a, right? The right-hand side is also 1 plus a. Therefore, they are equal. So the left-hand side is greater than or equal to the right-hand side. So let's focus on the inductive step. In the inductive step, we assume that this inequality holds true when n is equal to k. So we assume that 1 plus a to the k is greater than or equal to 1 plus k times a, where k is a positive integer. And then we will show that this is true when n is equal to k plus 1. That means we have to show that 1 plus a to the power of k plus 1 is greater than or equal to 1 plus what? K plus 1 times a. We replace n by what? By k plus 1. Okay. It is very important to figure out what we have and what we have to prove. So this is what we have, and this is what we have to prove. And it is also important to link what we have to what we have to prove, so that we will have a strategy to use the available hypothesis and prove that this is true. Okay, so it is quite simple, because 1 plus a to the k plus 1 is nothing but 1 plus a times 1 plus a to the k. That's a very important observation. Okay, this is similar to what we did before. Something to the power of k plus 1 is something times something to the k. Okay, and another observation is a is greater than or equal to minus 1. So you move 1 to the left, or you add both sides by 1. You see that a plus 1 is greater than or equal to 0. Okay, so this is true. Then we multiply both sides of this inequality by a plus 1. The new inequality holds true as well. So 1 plus a times this is greater than or equal to 1 plus a times this. Okay, and then And the right hand side here is nothing but 1 plus ka plus a plus k times a squared. Let's multiply out. 1 times 1, 1 times ka, a times 1, a times ka. So you have ka squared. Okay. So here we have something. Remember that k's are 1, 2, 3, 4, 5, and so on. The square of a number, like a squared, is always greater than or equal to 0. That's the most important observation here. So this is something plus a non-negative number, a number that is greater than or equal to 0. Like if you have 7 apples, you add 2 apples, so you have 9 apples. So you have more, right, than 7. Okay, so that means this is greater than or equal to 1 plus ka plus a, because this is something, and then you add a non-negative number. So this is greater than or equal to this. Think about this again. 7 apples, and then you add 2 apples. 9 apples have more. So it's greater than or equal to 7. And this is 1 plus ka plus a. So k orange. Oh, I use apple. That's right. K apples plus 1 apple. So you have k plus 1 apples, right? Okay, cool. So you see that based on the inductive hypothesis, this is greater than or equal to this. But this is nothing but 1 plus a to the power of k plus 1. I mentioned that earlier. And the right hand side is 1 plus k plus 1a. So from the inductive hypothesis, by multiplying both sides by a non-negative number, we see that this is true. So by induction, this is true for all n in n. Okay, so that's it. Please see my websites here. For more information, you will see more hints and solutions for this homework assignments. So thank you everyone for watching, and I hope everyone will be able to do well in the second homework assignment.